This is a lecture on magnetic circuits. And the analogy that we're trying to make here is that if we think about what we know about regular circuits, where we have a voltage and a resistance, and that gives rise to to a current, that we can use the same idea over here, where we have a magnetomotive force, which is equal to the number of turns on a number of windings, number of turns of the coil times the current flowing in the coil. And that is going to give rise to a flux which we will call phi. And the analog for the resistance in the magnetic circuit is the reluctance, the magnetic reluctance. Okay, so F is the magnetomotive force. Phi is the flux. And R is the reluctance. And then if we wanted to talk about the permeance, P, that would just be 1 over the reluctance. So we can, from this, we can write the equation phi is equal to Fp. So similar to our Ohm's law. And now if we think about an example core, ferromagnetic core. So suppose this is our ferromagnetic core. And it's got windings on it. Some number of turns N. I've got a current flowing in those windings. Then I can write the equation phi, the flux, is equal to mu Ni A over L sub C. And let's understand where all of this comes from. N again is the number of turns, and I is the current flowing in the coil. Okay, and that is, as we said before, the magnetomotive force. So in a minute we'll simplify this. A is the effective surface area of the core, and L sub C is the mean path length of the core. So if we make our effective surface area, and what these terms are doing are they're telling you about the reluctance of the core, right? So longer path length, less flux, larger surface area, more flux, right? These are reluctance terms. And L sub C here, the mean path length, is that path length if we were to go around the middle of the magnetic core, right? So this length is my L sub C, and this comes from this comes from Ampere's law. Mu, the term mu here, is the permeability of the core. And that is, to a large degree, a material property when the core is not saturated. And then just another value that we'll need is mu0, and that's the permeability of free space. And that is equal to 4 pi times 10 to the minus 7 henries per meter. If we want to talk about the relative permeability of a material, mu r, the relative permeability, that is equal to mu, the material's actual permeability, divided by the permeability of free space. Okay. So coming back to this equation, and I'm just going to rewrite that down here. We said that phi is equal to mu NIA over L sub C, and this is equal to, if I just pull the Ni out, it's Ni mu A over L sub C, which this again is equal to the magnetomotive force. So now I have F mu A over L sub C, and we know that phi is equal to the magnetomotive force divided by the reluctance. So therefore the reluctance must be equal to L sub C divided by mu A. Reluctances follow the same rules as resistances do for series and parallel calculations. And if we use these ideas, the simplifications that we're making here, to really take something that would be solved by Ampere's law using a path integral and solving it algebraically, we're going to get to within about 5% of the value, the true value, and that error, that 5% error, comes from a couple different places. One, we are assuming that the flux that is created by the current carrying coil of wire is all confined within the magnetic core, where in reality there is leakage flux outside the core. So if we just make a list of the assumptions that we're making here that are giving us a little bit of inaccuracy. One, we are assuming no leakage flux. Secondly, the mean path length assumption and the cross-sectional area are not 100% accurate, especially at the corners of the core. So we have a mean path length and cross-sectional area simplifications. Also, the permeability, we're assuming it to be constant here. So we're making a linearity assumption, but the permeability actually varies as a function of the amount of flux already in the material. So the assumption that we're making with respect to that is that the core is not saturated. Also, if there's any air gaps in the core, and we'll see air gaps in some of the problems. The effective cross-sectional area of the gap is larger than the cross-sectional area of either side of the gap. So there's that's called a fringing effect, and we can account for that to some degree, and you'll see that in some of the example problems. But we are making assumptions about the fringing effect. More on that later. So let's look at a quick example. An early example here. Suppose we have a core. And suppose I have 200 turns here. So n is equal to 200. And let's give some dimensions here. Let's assume the depth of the core is 10 centimeters. And then that's 30 centimeters. And I've got another 15 centimeters here. And this is 10. And this is 30. And this is 15, all in centimeters. And let's assume that the relative permeability of this core is 2500. And we want to find the flux that is produced if we have 1 amp of current. So we're going to divide the core into 2 sections to solve this. One section will be the side that is narrower, and then, so that's this side that is narrower. Notice this one is 10, where the leg is 15 everywhere else. So we have the narrower side. And then the other section will be the other 3 sides. And now we can compute the reluctances of those 2 sections. So we'll call the first one R1. And this will be equal to L1 over mu A1. And that is equal to, we need to convert everything to meters here. So it's 0.45 meters. And now divided by mu, well, mu would be mu R, the relative permeability, which we have here, 2500. And to get that to be mu, we need to multiply by the permeability of free space, so that's 4 pi times 10 to the minus 7. And then we need our area, and the cross-sectional area here is 0.01 meters squared. And the reason we're splitting this up into 2 sections is because we're going to get 2 different cross-sectional areas. Now, just a quick word about how we get this number 0.45. If we think about the mean path, again, going from here to here to here to here and here, then this point here is halfway, half of 15, so I'm getting 7.5 there. And same here, this distance here is half of 15. So I'm getting 7.5 there, plus the 30 in the middle. That's how I get 45 centimeters. If I compute this, I find that my first reluctance is 14,300 ampere turns per Weber. Now I'm going to repeat that calculation for the other three sides, and I'm going to call that R2. So that's going to be L2 divided by mu A2. And so that is equal to my length now in the numerator. And if I use the same idea and find the length from here to here to here to here, what I'll find is that I have 1.3 meters. In my denominator, I again need the permeability, so that's going to be the relative permeability, 2,500 times 4 pi times 10 to the minus 7th. And then the cross-sectional area for that portion of the coil is 0.015 meters squared. And when I calculate that, I get 27,600 ampere turns per Weber. So now I'm in a position to compute the total reluctance of the core. And so that would be R1 plus R2. And when I calculate that, I get 41,900 ampere turns per Weber. And so now I can compute the magnetomotive force. And that's just equal to the number of turns times the current. I'm told that I have 1 amp of current and that there's 200 turns. So this is 200 ampere turns. And now I've got the magnetomotive force, I've got the reluctance, I can compute the flux. Magnetomotive force divided by reluctance. So I have 200 ampere turns divided by 41,900 ampere turns per Weber. And so this equals 0.0048 Webers. We can take another example. Suppose we have a core now that has an air gap. This time we're going to have 400 turns. And here we are going to, I'm going to draw in the mean path going around the core, not including the air gap. So that mean path length, L sub C, we're going to say that's 40 centimeters. And also we're just going to, in this problem, the cross-sectional area of the core is going to be the same everywhere. So cross-sectional area of the core is equal to 12 centimeters squared. And now we've got this air gap here. And we're going to say that that air gap is 0.05 centimeters wide. Now, we're also going to say that we have a fringing effect here. So fringing in the air gap is going to increase the effective cross-sectional area by 5%. And just to talk about what's going on there a little bit, here's the idea. If this is kind of a zoom in of my air gap, and then there's flux flowing across the air gap, it all doesn't necessarily go in this straight line. You're also going to have maybe that as part of your flux path, right? And so it's more than just this area here in terms of the cross-sectional area of the flux path and the air gap, and that's what the fringing is. So we're just going to throw in a 5% factor there to say that at the air gap, my effective cross-sectional area is actually 5% more than the cross-sectional area of the core itself. Okay, so in this problem, we want to find two things: the total reluctance and how much current would I need to produce half a Tesla in the air gap. So if I draw my circuit for this one, I've got my magnetomotive force, which of course is equal to the number of turns times the current. And then I have a reluctance for the core, and I have a reluctance for the air gap. And so I can start to compute each of those. So if we start off with the reluctance of the core, the mean path length here is 0.4 meters. And I think what I forgot to mention up here is that mu r for this core is going to be equal to 4,000. So I have 4,000 times 4 pi times 10 to the minus 7. And this is going to be 0.0012 meters squared. And now if I compute through all this, I end up with about 66,300 ampere turns per Weber. That's my core reluctance. And now for the air gap, well, the length of the air gap we know is 0.005 meters. And now the reluctance of the air gap is simply the reluctance of free space. So that's 4 pi times 10 to the minus 7. And we want to multiply this by the cross-sectional area. Now that cross-sectional area that we had in the core, we need to increase that by 5% for the fringing effect. So we have 0.00126 meters squared. And this gives us about 316,000 ampere turns per Weber. Okay, so just like in the last problem, now I can compute the total reluctance. We'll call that R equivalent, equal to R sub C plus R sub A, and that equals 382,300 ampere turns per Weber. And that's part A, the total reluctance. For part B, we use the equation magnetomotive force equals flux times reluctance. And remembering that the flux is equal to the flux density times the area. and the magnetomotive force is equal to the number of turns times the current, I can rewrite this equation to be Ni equals BA, which is the flux, times the reluctance, and now I can solve this equation for I. I is equal to BAR over N, and what I want is B, the flux density, to be half a Tesla. So I can plug that in. 0.5 Tesla times the cross-sectional area where I want that 0.5 Tesla, which is in the air gap. So I use my adjusted for fringing cross-sectional area times the reluctance. This is the total reluctance, 382,300. I'll put the units in. Ampere turns per Weber. Divided by the number of turns, 400 turns. And when I calculate that, I find that I need 0.602 amps of current to get that half a Tesla in the air gap. All right, let's look at one more example. Try and look at a complicated example that has a lot going on. Okay, so here is a core. We're going to put the windings in the middle here, and we're going to have 300 turns. And now let me dimension this a little bit. All of these are going to be in centimeters. Obviously, this is not drawn to scale. Okay, so the shorter legs are 7, the longer legs are 30. Best seen here across the top, but we've got the same thing going on across here. This air gap is 0.07 centimeters, and we're going to make this air gap 0.05 centimeters. And the core depth is going to be 5 centimeters. We will assume that the relative permeability of the core is 1500. You see the dimensions. There's 2 air gaps, 0.05 and 0.07 centimeters. And we're going to assume that we have a 5% increase in area due to fringing at the air gaps. So we've got that going on. And again, we've got 300 turns in the coil. It's wrapped around the center leg. And we are going to assume a 1 amp current. So we have 1 amp flowing in the coil. And we want to know what is the flux on the left, center, and right legs of the core, and the flux density in each air gap. So we want the flux in each leg, and we want the flux density the air gaps. Okay. So for this one, we're going to have to divide the core into 5 regions. I'm just going to list them. R1 is going to be the left-hand portion of the core. R2 will be the left-hand air gap. R3 will be the right-hand portion. R4 will be then the right-hand air gap. And R5 will be the center leg. And now the thing to do is to just compute each one of these, but I want to write an expression for our total in terms of all of these. So it's going to be R5 plus R1 plus R2, R3 plus R4, I'm running out of room. This just comes from using the rules of series and parallel resistances. So there's my expression for the total, and now I can start to work out what each one of these are. So R1, this is my left leg, that's going to be equal to L1 divided by mu R mu naught A. Okay, and this is going to be 1.11 meters divided by 1500 times 4 pi times 10 to the minus 7 times 0.07 times 0.05. And what I want to do is I want to take this denominator term and let's just call it M. Or actually, let's just call it mu R mu naught A. Okay, so I'm not going to rewrite it every time. But at any rate, if I compute this, I get 168,000 ampere turns per Weber. Okay, so remembering, this is my relative permeability. This is mu naught, permeability of free space. And these two terms are giving me my area, my width times my depth of the leg. So now when I go to compute R2, I'm just not going to rewrite all that all the way over again. So this is going to be L2 divided by mu R mu naught A2. I'm going to call this one A1, this one A2. The difference between A1 and A2 is that I'm multiplying, or I'm increasing by 5%. So I'm just going to multiply that denominator by 1.05. So here my L2 is 0.007. I think I missed a 0 there. 0.0007. And I can just call this mu r, mu naught, A1, which is all of this, times 1.05. And that gives me the factor between A1 and A2, just so as to not rewrite all of those numbers again. This equals 152,000 ampere turns per Weber. R3 is the right-hand portion. So this is going to be, so we've got this symmetry here, so it's going to be the same as R1. So this is 1.11 divided by mu r, mu naught, A3, which is the same as A1. So this equals 168,000 ampere turns per Weber. R4 well, this is another air gap. This air gap path length is 0.0005 meters. And now I've got mu r, mu naught, and this area is going to be, again, multiplied by it's that, right? This is my original area, and this is just multiplying it by 5%. So the only difference between this one and R2 is that the gap width, or the mean path length, is a little bit different. So this gives me 108,000 ampere turns per Weber. And finally R5. So R5 is the center leg. And so my path length here is going to be 0.37 meters, mu r, mu naught, A. And if I compute this, I get 56.1 thousand ampere turns per Weber. So now I can compute the total reluctance. And so I'm just going to use this formula that we wrote up here that I found using series and parallel rules, and write my R total. I can plug those values in and get my R total, which is equal to 56.1. These are all thousands, plus 168 plus 152 times 168 plus 108 divided by 168 plus 152 plus 168 plus 108. And if I go through all this, and again, these are all thousands, I get 204,000 ampere turns per Weber. And now I'm in a perfect position to compute the total flux. So the total flux in the core is equal to the flux in the center leg, because that's where the windings are. So the flux in the center leg is equal to the total flux, which is equal to the magnetomotive force over the total reluctance. My magnetomotive force is 300 turns. It's 300 turns times 1 amp, so it's 300 ampere turns, divided by the total reluctance, which we just computed, so 204,000 ampere turns per Weber. and we find that what we have is 0.00147 Webers. The fluxes in the left and right legs can be found using basically the idea of a current divider. So we're going to use the current divider rule, but with the reluctances. So the flux in the left leg, that would be equal to R3 plus R4 divided by the sum, R1 plus R2 plus R3 plus R4 times the total flux. Again, this is a current divider equation. And if I plug the numbers in there and calculate it, I get 0.00068 Webers. On the right, I use the same idea, but now it's going to be R1 plus R2 in the numerator. Same denominator. Multiply that by the total flux. That's the portion of the flux that flows in the right leg, and that's going to turn out to be 0.00079 Webers. And now I can find the flux density in the air gaps. In the left air gap, that's going to be the flux in the left leg divided by the effective cross-sectional area. We've computed the flux in the left leg. We know the area is 0.07, 0.05, and we need to increase that by 5%. And when I do all this, I get 0.185 Tesla. On the right, well, my flux on the right was 0.00079 Webers, and I have the same area and the same fringing effect, and this gives me 0.215 Teslas. Okay, so the theory of how we use circuit theory to solve magnetic circuit problems, and then 3 different examples, going from a very simple example to an example with an air gap to a much more complicated example where I have to use series parallel resistance rules and current divider rules and all the things that we know from resistive circuits to find the values that I'm looking for and solve the circuit.